And our next speaker is going to be Dennis De, who is talking about the uniqueness of submaximally symmetric vector ODEs of C-class. Please, go ahead.
Okay. Thanks very much, and thanks to the organizers for the invitation to contribute to the program here today. So my talk today is based on joint work with my former PhD student, Johnson Kessie. Okay, so this talk is about classifying ODEs via symmetry. Okay, so let's let M and S denote the maximal and submaximal symmetry dimensions. Okay, and for the geometries in this talk, there's always going to be a unique maximally symmetric structure, and for ODEs, it's the one that you expect, just the trivial equation. Okay. But the goal is to locally classify all submaximally symmetric structures. I realized I forgot to specialize this. I'll specialize this to the C-class, and I'll define what the C-class is shortly. I guess a couple of takeaway messages from my talk. First of all, Boris Dubrov gave this excellent introduction to second-order ODEs the day before, so I wanted to follow up on that. And if you're learning it for the first time, then doing it the manner that he did it is definitely the way to go. But he did also mention that he's shying away from some of the algebra. If you want to go to the general setting that I'm talking about, so general nth order and systems, then you really need better control over what's happening with the algebra. So I want to kind of guide you to that and motivate it from the geometry and see where it gets us. Okay, so basically, the first half of the talk will be talking about the geometry of ODEs. Okay, what's the setting? Motivating the Cartan geometric perspective. Concerning this problem, when I say submaximal, operator, no homogeneity assumption is going to be assumed, but in the end, we'll get to a homogeneous classification problem. So for the second takeaway message, just for those of you coming into Cartan geometry, you might not appreciate this, but there's many equivalent descriptions of how you could even present a homogeneous structure. Okay, the most familiar would be the coordinate method, or just a coordinate model. Okay, so a differential equation as you're used to thinking about it. More abstract, for homogeneous structures, you could talk about Lie theoretic presentation. So you have the symmetry algebra F acting transitively. You have the isotropy at a point F0, and on that quotient of Lie algebras, then you have some F0 invariant structure. Okay, so we'll specify what this type of structure is, but that's another manner of presenting the structure. But what I want to kind of promote is this Cartan approach, what I refer to as Cartan theoretic. Even though everything's presented in terms of Lie algebras, it looks like it's a lot more data, but these are all equivalent. Okay? But the advantage, I guess, of working Cartan geometrically is that it allows for systematic classification. Okay? And methods here are not really specific to the ODE case. It's quite general. So if you're talking about any Cartan geometry, parabolic geometries, ODEs geometries, other geometries, these techniques can be applicable in those settings. Okay? Of course, the details of how to implement these strategies are specific to each of those cases, but there's ways of attacking, okay, that are quite similar to what I'm going to be talking about. Okay, so let's get to talking about symmetry gaps, okay, for higher order ODE. Maybe just the first symmetry gap, maybe not the first, but one of the first in the context of second order ODEs. So y double prime is equal to 0, as we saw in Boris's talk, has an 8-dimensional symmetry algebra, and it's SL3. Okay, so if you ask what's the submaximal symmetry dimension here, then it actually drops to 3. There's a large gap. Okay, so the study of these gaps has a long history, and I won't go through all the history here, but basically that's what we're trying to understand here. Okay. Also, though the techniques that I'm talking about, it isn't really specific to submaximal. Okay, you could go further down. Okay. But I'm going to concentrate largely on higher order ODEs. Okay, so there's this result due to Lie. Let's look at order 4 scalar mod contact transformations. I'll define contact. The maximal symmetry dimension occurring in the trivial model, trivial equation, is k plus 4, and there's a unique one. Okay. Submax, in general, you can have a drop by 2, except for 2 special cases. K is equal to 5 and k is equal to 7. There's only a drop by 1. Okay. There's also a classification results that's stated, for instance, in Peter Olver's book. So this submaximal dimension is realized by an ODE locally equivalent to a linear one, or exactly one of the following exceptions. Okay. So in k is equal to 5 or 7, you get some nice symmetry algebras popping up, SL3, SP4. Otherwise, you have some other equations. Okay. I'll just mention that everything in B here is in the so-called C-class, and I'll get to the definition shortly. But motivated by this, I mean, what about more generally? So what about for systems of, so I call them vector ODEs. C refers to contact transformations, P refers to point transformations. By the Backlund theorem, if I'm considering contact transformations, they're actually, for systems, equivalent to point transformations. So any contact transformation is the prolongation of a point transformation. Okay? Point transformation just being the transformations that you're most familiar with, so changes of variable just in the independent variable and dependent variable, and then prolonged up to the appropriate jet space. Okay, so the trivial equation has a symmetry algebra that looks like this. Okay, Vn is the nth fundamental representation of SL2, and then the maximum is so this dimension of this G. Okay, so let's classify some maximally symmetric structures. Classical methods that are used to obtain, for instance, these results are not really feasible. Okay, and I mean the general idea here is that Lie had this classification of Lie algebras of vector fields in the plane, and so from that list you could prolong them up to the appropriate jet space and start looking for invariant objects. Okay, but of course, I mean, getting classifications of Lie algebras of vector fields is not an easy matter. In dimension 3, there's been substantial work done. It's close to a complete classification, but I'm not sure if it's complete, but definitely not in, for dimension 4 and higher. Okay, so instead, what we're going to emphasize is a Cartan geometric approach. Okay, so geometry of ODEs. Okay, so let's work in this jet space. I'm using boldface for vector. Okay, so and on there, it's a locally Euclidean space that has some structure. Okay, this bunch of one forms. Contact transformations are diffeomorphisms that preserve this, and an ODE corresponds to a submanifold, codimension M. Locally, it looks like this. Okay, you want it to be transverse to the projection to the next jet space state. From this this data, this structure. We're going to pull everything back to this submanifold E, and we're going to get a rank 1 plus M distribution. Okay? So in the case of second order ODEs, we have a splitting into two line fields, but in general, so this is going to be rank 1, and this is going to be rank M. What is E? It's the annihilator of this pullback to the equation. Okay, so this is spanned by this total derivative looking vector field. What is V? It's basically the fiber to the next jet space down. Okay? Where is this coming from? It's coming from the Backlund theorem. Okay? That contact transformations on a general jet space are in general projectable over J1. So you start getting these distinguished fibers. Okay? The integrable fibers. Okay, so this is automatic. So you have these this splitting into a 1 and then an M. Okay? For talking about C-class later on, I'm going to refer to this solution space. So what is a solution space? I'm going to take this line field, this distinguished line field, and when I want to find integral curves of that, that's basically solving the equation. Okay? It's so when I pass to the local quotient, I'm talking about the space of integral curves of this line field. Okay? So that's S. Okay, so I have this distribution with a splitting. So we have a manifold with a distribution with a splitting. Okay, but just focusing on the distribution, let's start taking the weak derived flag. So take D, which I'll refer to as T minus 1. Bracket it with itself, get the level minus 2. Now for level minus 3, take that and always bracket with the original distribution. So that's the weak derived flag. Okay. Let's pass to the symbol algebra, so the associated graded. Okay. So as in take the successive quotients, and we're going to get structure relations looking like this. You always generate these new brackets. Okay. What's very convenient conceptually for me is this picture right here. Okay, so I'm going to think about this guy over here as like the d by dt guy, and this one as the partial un guy. Okay, and so this is split, and then this guy just generates this bottom row. Okay, so keep that in mind. I've drawn in red this dots over here. That's what encodes this extra data of splitting on the distribution. Okay, so we have a certain subgroup sitting inside the graded automorphism group of this symbol algebra. Okay, but keep in mind this picture. And then let's pass to talking about the flat model. So the trivial equation, I'll always be talking about this in sufficiently high order. Okay, so for scalar, that means order 4 and higher. For systems, order 3 and higher. Okay, so generally, we're going to get this symmetry algebra when you do the computation, when you analyze the structure of the symmetry algebra. So as I mentioned, this Vn is the nth fundamental representation of SL2. Okay, so the stabilizer at a point gives you this subgroup right here, so special triangular matrices. Okay. For later on, I'm going to define this Q, okay, so enlarge this a little bit more to this SL2. But so we've just enlarged that picture on the previous slide by this extra direction over here, okay, one extra dimension. Okay. So this XHY is an SL2 triple, and then you have these matrices EAB. That's corresponding to the GLN piece. Okay. These dots, so this is one-dimensional over here. These dots are in general m-dimensional each. Okay. So, but just to emphasize the grading, what we have here is a non-symmetric grading for these higher order guys. Okay. It has a long, quite a large depth, but just a very short height. Okay. One extra dimension spanned by this y. Okay. Associated to this, we're going to induce the corresponding canonical filtration, G superscript I. Okay, so filtration, that's the smallest filtran. Then you have the next larger, then the next larger, keep going. So it's a decreasing filtration as you increase the index. Special so-called parabolic cases where you have symmetric grading are the following. So here I have this, this bit that looks like what we have up there, but in this case there's actually more bits to the symmetry algebra. You have these extra bits coming up here. So instead, so you have grading 1 over here, as well as over here, then grading 2, grading 3. Okay, and you get a symmetric grading over here. So that's for third order ODEs. You get SP4 symmetry. This is the root diagram there. Over here you get SL3. So this is second order ODEs, but you have to change instead of contact transformations, you talk about point transformations. Okay, so -2, -1, -1, 0, 1, 1, and 2. So in low order, you get some special phenomenon happening. Okay, so here's the big theorem that Boris mentioned, that he and Konrakov and Morimoto proved in 1999. Canonical Cartan connections of type GP that I specified before, exist for scalar ODEs and systems of ODEs. Okay? So this realizes, general ODEs as curved versions of the flat model. Okay, the flat model being corresponding to the trivial equation. But a key point, a Cartan connection is a coframing, also called an absolute parallelism. So when you talk about symmetries, either downstairs or reinterpreted upstairs, okay, symmetries downstairs, and then this is reinterpreted upstairs as vector fields that are P invariant that preserve the Cartan connection. Okay, those are the same. Okay, but one result is that for an absolute parallelism, that the symmetry dimension is bounded by that dimension on which the coframing is supported. And this bundle, this total dimension here is G, the dimension of G. Okay, so this gives us an upper bound, which is in fact realized for the trivial. As usual, you get the tangent bundle downstairs being an associated bundle. So all P invariant objects here, they transfer geometrically to subbundles or geometric objects in the tangent bundle. You have the curvature, you have the corresponding curvature function. It's horizontal. Right? There's a lot loaded into this statement, canonical. Okay, so in parabolic land, you talk about regular normal. Okay, so regular means that if you look at homogeneity, so I defined a grading, the previous slide. There's a grading element that induces that grading. And so regular just means that if I let that act, that grading element, then it acts with positive homogeneity in places where kappa lives. Normal, there's a codifferential that provides a normalization condition. Basically, it's just, so it's a restriction on where kappa can live, so that you have this equivalence of categories. Okay? But moreover, there's a fundamental part of this curvature called harmonic curvature. Okay? And there's a lot in this story. I'm not going to get bogged down by it right now. But basically, the place where harmonic curvature takes values is a certain second cohomology space. Okay? Positive with respect to, because of this regularity condition. And there's also a harmonic theory behind this. You have corresponding to this cohomology certain harmonic forms. Okay? So correspondence with these cochains on G minus with values in G. A subtlety in the ODE setting, unlike in the parabolic setting, is that actually not all regular Cartan connections of type GP come from ODEs. You have to be careful here. So, I mean, basically we have what's called a manifold with a distribution and some reduction of structure encoding that splitting. There's an equivalence of categories for that type of geometric structure, of which ODEs are one particular type. But there's additional sort of integrability conditions coming from the fact that ODEs live in jet space. There are these distinguished fibers from Jn+1 all the way down to J1. Okay, so you have certain necessary integrability conditions, involutivity conditions, right? So, but I'm not going to be too precise on this right now, but it is something that just to keep in mind. Okay? Let me define a little bit more of this C-class. Okay, so Cartan, so it goes back to a paper of Cartan, a short 4-page paper, only 4 pages, in 1938. And he formulated it as follows. So you specify a transformation group. Okay, so you contact transformations. A contact invariant class of ODE is a C-class if for each ODE in this class, all differential invariants are first integrals. Okay? I had to specify a little bit more what differential invariant means, but and how he was meaning it was, so at least for the examples that he considers, so second order ODE and scalar third order ODE, there's a Cartan connection. There's curvature of the Cartan connection, and that curvature transforms in a certain way under the structure group. Let's take some functional combinations of the entries of those the curvature, such that you get an expression that descends down to the base. Okay, so it's invariant under the action of the structure group. Okay, so that's what he's viewing as differential invariance, stuff that comes from the curvature. Okay, and we want these to be constant on solutions. Okay, why is this useful, and why was he interested in it? Well, basically, you could think of this as being kind of the opposite to talking about ODEs that have a lot of symmetry. Imagine an equation that has no symmetry at all. It's generic, but it's in this C-class. So the curvature, there's a lot of functionally independent stuff there. Okay? But if you have a lot of those, and they're all first integrals, or differential invariants there are first integrals, it's in this C-class, you could use that to solve an ODE. Okay? Without any integration. Why do I say without any integration? Basically, in building a Cartan connection, you run the method of equivalence. All that you're using is exterior derivative, linear algebra. You're not using any integration. Okay, so obtaining a Cartan connection, obtaining curvature uses local operations. Okay, so that's the hope, the spirit. I mean, why it's useful. In practice, it's kind of difficult to write one of these equations down. So that also motivated, like, okay, what are some equations in this C-class? I mean, the ones that I'm going to talk about have a lot of symmetry, so it's kind of, yeah. Anyways, how do you characterize the C-class? Okay, so this is work with Andy Chap and Boris Dubrov from 2017. So the modern formulation of C-class is that this canonical Cartan geometry associated to the ODE, it descends to the solution space. Okay, so you have E, and then you have this quotient S, okay, and then you have this bundle, okay, and this is the structure over here. So the question is, when you perform this quotient, can you descend this? Okay. Of course, there are conditions for being a Cartan connection. You have to have a certain equivariancy condition. You have to have curvature being horizontal. Those are consequences, right? So what do we need to do for this to descend down to the solution space as a Cartan geometry of, well, a different type, okay, Q. And it turns out that you could formulate this just in terms of curvature, that if you insert that x direction into curvature, it should be 0. Okay? So for those of you that are familiar with Andy's correspondence at the twistor space paper, this is very much in the spirit of that. Okay? And So if you take that as the definition of C-class, then here's a characterization that we proved. An ODE is of C-class if and only if it's Wilczynski flat. Okay? All generalized Wilczynski invariants vanish. There's explicit expressions for these Wilczynski invariants. I'm not going to give them right here. I want to focus on where do these Wilczynski invariants live. Okay? Give you the panorama of what all ODEs, how they're classified in an invariant way. But just a small digression, I guess, before I get to that. If the Cartan geometry descends, this is also linked with the existence of geometric structure on solution spaces, which was quite an active topic maybe about 15 years ago, Pavel Norovsky and his collaborators, for instance. Okay? So for instance, let's just look at it in terms of the model. We have this picture. If we're going to quotient, then basically what goes into the isotropy is this x direction. In the scalar case, this is GL2. This is the tangent space to the solution space. So this is a GL2 representation. Okay? And on the solution space, you get what's called a GL2 structure. Okay? So the orbit of so you think of it as the tangent space to your solution space as nth order homogeneous polynomials in two variables, and then this minimal orbit of pure nth powers, that's a rational normal curve of degree n. So that's a way of formulating the GL2 structure. If the dimension of this space is even, you get as a consequence of that the existence of a distinguished conformal symplectic form. If it's odd, then you get the existence of a distinguished conformal structure. Okay? So that's coming from SL2 or GL2 representation theory. In the vector case, these are all thickened, right? These are m-dimensional, and you get a certain Segre-Veronese variety as being the structure in each projective tangent space. Okay, so we have this G split into two levels over here. So we have this Q and then this abelian part over here. All right, so what's now the landscape of harmonic for vector ODEs? Okay, so we're going to look at this H2 guy, and so work due to Sasha Medvedev and Boris Dubov. Okay, so for vector ODEs, the harmonic curvature is valued in a certain subspace, which we'll call the effective part, and it decomposes it into the following irreps with respect to G0. Okay, so we have certain labels here for what I call the Wilczynski part, and then you have the C-class part over here. Here, instead of grading, I'm talking about bigrading, right? We have a splitting into this E and V. So you could actually find two central elements at level G0 such that E has, so a Z1 and Z2. So Z1 acts as, say, -1 over here and 0 over here, and a Z2 that acts as -1 over here and 0 over here. So you can induce a bigrading. Okay? Just a finer way of classifying what's going on here. Okay? So if you're in C-class, the Wilczynski invariants, which take value over here, have to all vanish. And so all that's going to concern us is what's happening over here. Okay? The different labels here, I guess I'm just organizing it with these different letters based on what the Z2 grading is here. 0, here it's 1, so I call them A, and then here's Z2 is 2. Okay? So you have how these central elements, say Z1 and Z2 are acting, but then you have the semi-simple part, SLM, and what this is as a representation. Okay? So this representation theoretic information is really what's going to get us going. Unlike in the parabolic case, which also you get a nice description of H2 through Costant's theorem, so there's a further information about what the lowest weight vectors are for those irreps as harmonic two cochains. Okay, that information was not known here, so in order to do classification, we really need to fill in this information. Okay, so for each of these C-class reps, we were able to find it and give explicit realizations for lowest weight vectors as harmonic two cochains. A little bit more complicated than, quite a bit more complicated than in the parabolic case. I'll give you a glimpse of what these look like later. Okay, now I can finally formulate a theorem that we showed. So over R, below is the complete local classification of vector ODEs C-class that are submaximally symmetric relative to one of these irreducible representations. So here it's for B4, A2 trace free. Here are the numbers, and then you have certain explicit coordinate models. Okay? Over C, these models here, in fact, collapse. Okay, they're locally equivalent. Just as a remark, when you specialize this to the scalar case, so these third-order ODEs have SO22 and SO13 symmetry. If you look more broadly, not just in the C-class, so our first paper with Kessie, we did the enumeration problem. So we established that S is equal to m minus 2. You don't have these different exceptions like you do have in the scalar case. This can also be realized this is generally realized in the Wilczynski branch, okay, the so-called trace Wilczynski type. Yeah, this one right here. But if you look at these numbers carefully, then you'll notice that you could also do it in the case of third order pair of ODEs in this B4 branch, so when m is equal to 2. Okay, so kind of a summary of recent study of gaps. Well, yeah. So for parabolic geometries, so my work with Boris Kruglikov. Okay, so we proved some results. So the results were the following. Just a quick summary. So the submaximal symmetry dimension is bounded by an algebraically defined quantity. Okay, U. This is defined via representation theory. I'll define it shortly. Okay, but this is geometric over here. This is algebraic over here, and we have adapted versions for each irreducible component inside H2. What about being able to compute these U numbers? Okay, so when G is complex or it's split real with rank at least 3, we were able to establish that S is equal to U. Okay, it also works for some rank 2 cases, but you can have exceptions where they're not equal. Okay. Also, as soon as you move off of complex or split real,
What is U?
I know. I said I'll define it shortly. Either next slide or the slide after that. There are efficient Dinkin diagram recipes to be able to find U. Costin's theorem, as I mentioned, is crucial in this story. In his work with Kessie, this first work with Kessie, for ODEs about contact, we similarly established this. ODEs is a nice setting that you have this harmonic theory. So a lot of ideas over here, you might suspect transfer over, and it does. Okay, in the scalar case, we gave a modern proof of this, okay, independent of classification of Lie algebras of vector fields in the plane. In the vector case, we established this and results for each one of those other irreducible components of H2. Okay, and we use this effective part, as I mentioned, computed by Boris and Sasha. One thing that you could show is that when these two numbers are equal, when S is equal to U, then any submaximal structure is locally homogeneous in a neighborhood of a point where harmonic curvature is non-zero. Okay, so now the question becomes, how do you classify submaximally symmetric homogeneous structures efficiently? I'll just emphasize here, like in both of these works, we didn't focus on the enumeration of all structures in that submaximal strata. We established this upper bound, and then can you find a model that whose symmetry dimension realizes that? Okay, so this is what these. I wrote a paper a few years ago about classifying, whether you have uniqueness for these submaximal guys in this complex or split real case, and then what I'm talking about today is in the ODE case. Okay, so let's define U. Okay, so let me talk about extrinsic Tanaka prolongation first. Okay, so let G be a graded Lie algebra, with the negative part being generated by G minus 1. Let's let phi be a vector in a G0 representation. Okay, so H2. Let A superscript phi be the graded Lie subalgebra with the following prescription. The non-positive part, you have the negative part full, the level 0 guy reduced as the annihilator of phi, and then you propagate that up to the higher levels. Okay, so level 1 consists of those vectors that bracket with everything in level G minus 1 to live in level A0, okay, the annihilator. Okay? And then you just keep propagating it up. Okay, so it's adapted to this vector that you're prescribing as input, this phi. Okay, now let me define U. Okay, so given this submodule sitting inside the effective part, let's define the following. Okay, so the maximal dimension of this Tanaka prolongation for a non-zero input. Okay, so a nice algebraic definition. Okay, maybe this will have zero component in the positive part. Maybe there will be some positive prolongation. Okay, that has to be computed. S is this geometric quantity, the dimension of the symmetry algebra where the harmonic curvature is prescribed to be concentrated in this U piece, but non-zero. So for parabolic geometries and ODE mod contact, you have this inequality. Okay, and as I mentioned before, when these are equal, all submaximally symmetric models are locally homogeneous near a point where capital H is non-zero. Some specific calculations for the U's that I had in the table. Okay, so first of all, I mean, do I need to test everything in that module? No. Okay, so it turns out, there's an argument, representation theoretic, that it's sufficient to just check the lowest weight vector. Okay, so here's the results for these different modules. For B4, for third order ODEs, you get into positive prolongation. Also for this third order guy, but in this different branch, you get into positive prolongation. But for the other cases, you don't ever get into positive prolongation when that input is non-zero. Okay? This is really also, when you talk about the scalar case, why do you have these exceptions in for order 5 or order 7, right? You're going to get into positive prolongation, basically. The cohomology that you compute there is different in those dimensions, and there's some specific modules that at least in level 0, you're going to get an H. Okay, so that when you bracket Y with the X, you get it's compatible. Okay, so now to show that these are actually equal, I mean, you calculate the dimensions based on this, but you need to find a model. Okay, so you need to exhibit one. How do you do that? Sometimes a good guess will work, and then you can check it using Maple. How many do you have? But if you don't have a good guess, you have to be more systematic. You got to classify. So a strategy here that I'm going to talk about is to classify abstract structure first. Once you have that, then you can talk about integrating it to find a coordinate model. Okay, so what is this Cartan theoretic description that I talked about? This is in section 1.5 of the Parabolic Geometries book. How do you encode a homogeneous Cartan connection? Okay. Well, so imagine I have a symmetry group acting from the left, right? And then I have this structure group acting on the right. Okay, so we get a transitive action by F and P everywhere there. Everything's determined by its value at a point. Okay, so here's this homogeneous bundle over a homogeneous base. Okay, what's the data? So I call it an algebraic model. It goes by some other names, but an algebraic model. So FGP, so what is this? It's a Lie algebra such that first, F is a filtered subspace. I'm going to assume G and P are as given, and I have this filtration there. So I have this F sitting inside there, and I inherit the filtration. Okay, it's a filtered subspace. Okay, so I just inherit the filtration. But now let's take the associated graded. Let's call it S. And I want to prescribe that S minus is G minus. Okay, so I'm dealing with a transitive model. Okay, so F mod F0 is G mod P as a consequence of this. Second condition, a consequence of equivariancy, okay, in the definition of Cartan connection, is that the isotropy, so F0, it inserts trivially into the curvature. What is curvature? It's the deformation of the bracket. Okay, so for F0 stuff, then this is 0. So the ambient bracket on G is the same thing as the ambient bracket, as the F bracket. Okay, when you insert an element F0. So that means this kappa that I've defined here, it descends to an element over here, and then you use this isomorphism to get you into familiar territory. Okay, where it lives. Then you have this regular normal condition. But when you do this, right, when everything's determined by its value at a point, because of that equivariancy condition in the definition of Cartan connection, as I move up and down the fiber, things transform equivariantly. So this is good to be aware that, okay, sorry, M, the set of all algebraic models, it admits a P action. Okay? Sorry, I skipped this, but so M is furthermore partially ordered. Maybe the model that this F that's given isn't the full symmetry group. Okay, so we're going to say F is less than or equal to F prime if this includes into that as Lie algebras. Okay, we're always looking for maximal elements with respect to this partial order, but we have this freedom to, by P, of which how to present things. Okay, so really we're classifying these algebraic models up to this P action. Okay, but that's still abstract. How do you actually get started? And how do you link this with harmonic curvature? So here's a little proposition. Okay, so let this be an algebraic model. This is a filtered Lie algebra. Its associated graded is a graded Lie subalgebra. F0, we know, inserts trivially into curvature, but it also annihilates curvature. Okay? So more explicitly, that's what it means. But also, now here's the link with harmonic curvature. This associated graded, this S, it sits inside this Tanaka prolongation with harmonic curvature shoved in. We also say that F is a filtered sub-deformation of this Tanaka prolongation. So you take a subspace, and then it's some filtered deformation. Okay? So this distinction between filtered and graded is really crucial here in doing classification and understanding what these models are. Just a couple points. So first of all, a warning. It's a filtered Lie algebra, but it's not a subalgebra of G. You have this deformation by curvature. Next, how do you actually get started with doing classification? You look at this constraint that's given to you by harmonic curvature. And we're going to let harmonic curvature be in one of those irreducible modules, U, from before. What this is doing, right, in looking at associated graded, you're getting information about the leading parts of F. Okay? What you need to do is figure out what the filtration tails are. That's the task. There's a theorem also showing that while the leading parts of the curvature, which is part of that description of algebraic model here, the leading part, so in lowest degree of homogeneity, is harmonic. Okay, so you have the harmonic part, but what are the higher pieces, the filtration tails, the curvature? Okay, so let me just summarize what things look like for vector ODEs of C-class. Okay, as I mentioned, we needed to first understand what are the harmonic parts. Okay, in the constant setting, right? What these lowest weight vectors are, you have nice decomposable vectors looking like this. Okay, two cochains, really nice decomposable. It's a little bit more complicated in the vector case. Okay, so this formula here, I mean, it was I think in Sasha's paper from 2013 or 14 when he studied the third order ODE case. This took some effort to find. Okay, could tell you some more details, but just it's complicated. Okay, so this is there are further details that you need to further conditions that you need to post to help you narrow down your search for what this is. So as I mentioned, yeah, so not all regular normal Cartan geometries of type GP come from ODE. There's further conditions. There's something called a strong regularity condition. There's another condition that we refer to as the Dubrov-Medvedev condition. Okay? So if you combine all of these and knowledge of the weights, okay, say the bigrade, so you get a nice ansatz first using the bigrade of, so look at this. So something looking like J's that I defined over there. Okay. Okay, so knowledge of the bigrade gives you a nice ansatz, and then imposing those conditions, you get to some nice recurrence equations on these coefficients, and you could use that to find these explicit expressions. Okay, but now here's an example of what those algebraic models look like in the case of ODEs. Okay, so for F, the simplest thing that you can hope for is that F is equal to this Tanaka prolongation as a vector space. But you just have curvature turned on. Okay? And actually, for the parabolic cases, that was successful. So in the story with Boris, right, you have these lowest weight vectors. You compute this Tanaka prolongation. Okay, you set this equal as vector spaces, but then you deform the bracket. So you have this F is equal to this deformed by curvature. Okay. Well, you see, does that work? Does Jacobi hold? And it does hold when it's well defined. So when this is valued over here. When do you have exceptions? You have certain exceptions in the rank 2 cases. Okay? But if you're in rank 3 or higher, then it turns out this is all well defined, and Jacobi holds. Over here, you have a similar story for these cases over here. Here you could try to use a structure group, this P, to normalize things further, but it turns out you can't get rid of it in the real case. Okay? But here it's basically very similar in spirit to what we did with Bors. Okay? Where things were very different, much more complicated in this non-parabolic setting, is in this trace case. So we had to work quite hard here to figure out what's happening. But here there's a filtration tail. Okay? So you have this x. This is at level 2, okay? By grade 1, 1. Here this is by grade 2, 2, level 4. Okay? So this is of this form. And then you have these guys at level 0, but with no filtration tail. You have these guys at level minus, part of A, I guess. And you have some filtration tails over here. Okay? So you could get to this form basically using as much as possible these linear conditions that I mentioned. This strong regularity, this Dubrov-Medvedev condition. And so you get to a few parameters that are left over. What do you have to do to finish up the story? You impose Jacobi. Okay? So Jacobi identity shows you that these parameters are uniquely determined functions of n and m. So there's a unique model here. Unique model here, and most 2 models. Or, if you're in the complex case, then you'll have uniqueness there. But of course, remember that not all of these Cartan geometries come from ODEs, so you do need to check. Okay? Can you find an ODE? So to match this with the aforementioned coordinate models, we're going to verify, first of all, that harmonic curvature is in the correct branch, using the explicit invariance in coordinates that are known, but also that the symmetry algebra is equal to the submaximal. Should be SU over here. Should also mention one more thing. So classically, there's a method called Cartan reduction used to find models. Okay. But in setting that up, I've done one of these problems before with the Legendre contact in dimension 5. You need to know full structure equations. Like, what is the subspace in which curvature is valued? You put undetermined coefficients. You select which harmonic curvature type you're working with. Examine that branch. Look at the action of the structure group, blah, 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 blah. But you need to start out with full knowledge of the structure equations. In what I'm talking about here, in not working in this form language, but using representation theory on the other hand, we're circumventing this. Okay? You don't, and in fact, so very, very little of del star is used. The only place where del star is used is right here. So you could get to this point by imposing those linear conditions that I mentioned, but the final step is finding the relationship between alpha and beta. That's where some knowledge, just a little bit of knowledge of this del star is used. But other than that, it's difficult to write down del star in a complete expression for it. Okay, so we try to avoid that as much as possible. Okay, so so you don't need full structure equations. You want to take advantage of representation theory. Okay, there is of course the detail of like how do you get these forms, right? Basically, oh sorry, no, I'm gonna stop right here. So yeah, thank you.
So, do we have 1 or 2 questions or comments for Dennis? Yes.
So in scalar exceptional cases,
Yep.
do you need full structure equations?
Figure that out.
No, not even that.
No.
Anyone else?
Do the prolongations that appear in most of them seem to not have positive degree, but some
Yep.
do.
Yep.
Do they all stop at first degree, or do some go?
Well, so in the model, it stops at first degree, so you're not going to get any higher than that.
Or,
Right. Yeah, and it's precisely the 5th and 7th order where you get into positive prolongation.
Yes.
Yeah. So that's one way of characterizing that phenomenon algebraically. So you have an H inside your annihilator, corresponding to those harmonic curvature functions.
So, let us thank Dennis again. And we will start in 2 minutes at 16:47.
You're very nice.